Here is another example where we have to combine more than just one technique. As you know, when you've got fractions, we try to factorise the denominator as best we can, and here we've got x cubed minus 1. Now, that's the difference of two cubes. The pattern for the difference of two cubed, if you've got a cubed minus b cubed, it factorises to a minus b. That's sort of a squared plus ab plus b squared. You also should know that the sum of two cubes factorises to a plus b. That's sort of a squared minus ab plus b squared. You can verify those by multiplying the two factors out, and you should get the left-hand side. So here we've got x cubed minus 1. Now x cubed minus 1 can be written as x cubed minus 1 cubed. And so using this pattern here, it's equal to x minus 1 outside of x squared plus x plus 1. So we can factorise the bottom, so there's a good chance we're going to be able to use partial fractions here. So if we just look at the integram, what we're trying to integrate, we've got 3x squared plus 2x minus 2 over x cubed minus 1, and that's equal to 3x squared plus 2x minus 2. The numerator stays the same, but we've been able to factorise the denominator, and that's x minus 1 sort of x squared plus x plus 1. And so we can split into a over x minus 1 plus, this is non-reducible anymore, it won't factorise. No matter what method we use, we can't factorise that. So it's what we call a non-factorisable or non-reducible quadratic. So with those we put bx plus c on the numerator, and we get x squared plus x plus 1. So we'll still split it into two fractions. And using methods that we've used before, I'm not going to go through this now, but previous little mini lectures have gone through how to actually find a, b and c, and we use those same techniques to come up with a equals 1, and b equals 2, and c equals 3. Okay, so now what we can do is, to do this integration, we can say the integral of 3x squared plus 2x minus 2 over x cubed minus 1 with respect to dx is equal to the integral. Now we've identified that a is equal to 1, so it'll be 1 over x minus 1 dx plus the integral. Now we've got bx plus c, b is equal to 2, so that'll be equal to 2x plus 3 over x squared plus x plus 1 dx. Okay, so this is fairly straightforward. The integral of 1 over x minus 1 is equal to ln of the absolute value of x minus 1. Now, at the moment, this is non-reducible, x squared plus x plus 1, and we need to develop a technique to be able to resolve this. So what we can do, if the top here was the exact derivative of the bottom, so the derivative of the bottom is 2x plus 1, if that was 2x plus 1 up there, we could just use substitution with u equals x squared plus x plus 1, and we would find that we'd get rid of this top and it would all work out. But unfortunately it isn't. 2x plus 1, the derivative of the bottom, it's 2x plus 3. But that would give us a little bit of a lead into where we go from here, because we can split 2x plus 3 into 2x plus 1, which is what we want, over x squared plus x plus 1 dx. Now this numerator is 2x plus 3, so we've only got 2x plus 1 on that fraction, so if we put another 2 over that, when we combine those two fractions together, we'd actually end up with 2x plus 3. So we'll just remember that line, because what I'm going to do now is go through each of these two integrals individually, and then we'll put the whole thing together right down the bottom. Okay, so let's firstly look at this one over here. So we've got the integral of 2x plus 1 over x squared plus x plus 1 dx. And if we let u equals x squared plus x plus 1, the denominator, we know that du dx, derivative of that is 2x plus 1, which is what we were hoping for. And we're going to do a substitution here, so we need to find out what dx is. So we can say that du over 2x plus 1 equals dx. We've now set up, ready to go with substitution. So my integral of 2x plus 1 over x squared plus x plus 1 dx is equal to the integral. We will not change that at the moment. Hopefully that's going to cancel out. We've replaced all of that with a u. Don't need that big long line there. Times now dx. Instead of dx, we've got du over 2x plus 1. Okay. Yes, they do simplify. The integral of 1 on u with respect to u is ln u. ln. Now u was x squared plus x plus 1, and it's the absolute value of that. Alright, so we've actually calculated this integral here. Now we'll have a look at this one over here. So we've got the integral of, now if the 2 is out the front, sorry, we can take that 2 out the front, so we can put the integral of 2, 1 over x squared plus x plus 1 dx. So all I've done is just taken the numerator out the front. The way of coping with these, we've seen once again in previous work, is the fact that we can use completing the square because we've got 1 over quadratic. So let's go through with completing the square. You've got x squared plus x plus 1 is equal to x squared plus x. Now it is half the coefficient squared you've got to add, so it'll be plus a half squared. The coefficient of x here is 1, half of that is 1, and if we add, we've got to subtract, so we keep the same value, and then we've got the plus 1. Now what that allows us to do is complete the square, and it's just x plus a half all squared. So if you multiply that out using 4, you'll get x squared plus x plus a quarter. A half squared is a quarter. Now we've got minus a half squared, so the minus is outside. We've got to square the half to get a quarter, and then minus a quarter plus 1 will be plus 3/4. So 2 integral of 1 over x squared plus x plus 1 dx is equal to 2 integral. Now we've completed the square here. It'll be x plus a half squared plus. Now the pattern we've got to get it into is like x squared plus a squared, and then we'll get our arctan. So we've got 3/4 here. Now what have we got to square to get 3/4? Well, it'll be root 3 on 2 dx. We know that the integral, one of our integrals we need to remember, x squared plus a squared dx is equal to 1 on a arctan of x on a plus c. One of the rules that has been suggested to learn off by heart. The integral 1 over x squared plus a squared dx is 1 on a arctan x on a plus c. So here, so my integral my x here is x plus a half. My a is root 3 on 2. So it'll be 1 on A, so it'll be 1 over root 3 on 2. Arc tan of x on A. My x is x plus a half. Well, my A is root 3 on 2. Plus C. That can be simplified. When we divide by a fraction, we multiply by its reciprocal, so you get 4 over root 3. 2 times, when I divide by that, I'll get 2 over root 3. 2 times 2, 4 over root 3. Arc tan, x plus a half, all over. Now root 3 on 2, once again we're dividing by a fraction, so we multiply by its reciprocal. So that'll be that multiplied by 2 plus a constant. So 4 over root 3 arc tan. When I multiply this by 2, I get 2x plus 1 over root 3 plus a constant of integration. So if we go back up, so we've simplified the last integrand to that. So we should put this in brackets because it'll be arc tan of that. If we put it all together now and go right back up into this equation here, the required integral of the original question was the integral of 3x squared plus 2x minus 2 all over x cubed minus 1 dx. That's equal to, so if we go back up here, there's the original, and it was equal to ln plus the integral which we found, and then that integral which we found. So putting it all together, we've got that as equal to ln natural log of x minus 1 plus this second integral here, we evaluated to ln x squared plus x plus 1. And then the third one was 4 over root 3 arc tan 2x plus 1 on root 3 plus a constant of integration. So this has combined a number of steps. We've basically used partial fractions, and then in using partial fractions we've also had to cope with the fact that we've got an irreducible quadratic as a denominator, and the way to cope with those is to complete the square, and we've come up and put it all together in our answer.